So, hello everyone. Can you hear me? I hope it works now. Just a moment. I don't think my slides are shared. Perfect. So, hello everyone. Sorry for the technical issues. I hope everything is resolved now. So I will give you just a short introduction into the workshop, and then we will directly proceed with our program. So my name is Jan Biška, and together with Michal Krone and Björn Sommer, we are organizing this workshop already for the third time in the row. Seeing all of you here makes me happy to see that it's growing as it is. So as every year, we have invited this year also short papers and full papers. And in the end, we ended up with selecting 2 full papers and 2 short papers for the program. This would not be possible without the great paper from all around the world. So I would like to thank to our International Program Committee, who despite the problems caused by the coronavirus, managed to review and read the papers and submit their proposals in time. So how you can participate? There are 2 channels. Primarily the YouTube channel, where you are watching the chat now, or in the Zoom as a backup solution for our first session. You are also welcome to join our Discord channel, and you can ask questions both in the YouTube chat or in the Discord. The chairs of the sessions will collect your questions and ask the speakers on your behalf. Also, if possible, for instance, in the Discord channel, if you see a question which you would like to see answered, maybe mark it with thumbs up or some other smileys, so it's easier for the chairs to pick up the great questions. Today we will have 2 invited speakers. In the first session, we will have Mathieu Linares, and in the second session we will have Pere-Paul Vasquez. So maybe let me just shortly introduce Mathieu. He obtained his PhD in the theoretical chemistry in 2005. After that, he went through different positions as a postdoc. So first he joined the Laboratory of Chemistry of Novel Materials in Mons, where he was doing modeling of self-assembly in solutions and surfaces. After that, he became a postdoc in computational physics group in Linköping University in the years 2008 and 2009. Then he joined theoretical chemistry at the Ural Institute in Technology in 2010. And he is now working as the associate professor, and this position is shared between the Laboratory of Organic Electronics and the Group of Scientific Visualization at the Linköping University. So I'm really looking forward to his talk about the interactive analysis of molecular dynamics. So I guess with respect to time, I just now give the floor or the stream to Mathieu.
Jan, you need to unshare your screen so I can share my screen. All right. Can everyone see my slides? Can I get a thumbs up, Jan? Do you see my slides? Is it okay? Can I start? Sound is good? All right. Thank you. Well, thank you all. Thank you, Jan, for the introduction. Thank you all for joining in. So today I will talk about visual interactive analysis of molecular dynamics. So as Jan explained, I'm a theoretical chemist. I did my PhD in France, and then I moved to several postdocs. And in 2011, I became a lecturer, assistant lecturer in Linköping University. And this position has been supported by the SERC, the Swedish E-Science Research Center. And I will tell you a bit more about it in the next slides. So within this SERC, I started to collaborate with the visualization group in Linköping. And this collaboration had been rather fruitful since I finally joined them, at least partly, 50% of my time, since September 2018. So our collaboration started with SERC, which is a non-physical center, which has the goal of promoting e-science. And e-science, it's encapsulates the research that needs large-scale computing and data resources. And e-science, this is the use of this digital information and the processes of this information to gain new scientific insights. So what is SERC? SERC, so it's a research center, as I told you, that is one of the 24 strategic research area in Sweden. And it has been funded by the Swedish government. And since 2010, and it's collaboration between 4 universities, KTH, Stockholm University, Karolinska Institute, and Linköping University. So the funding, the first funding was of 30 million crowns per year. And since then, well, it has been working quite well with, pretty good number of PI. Now we have 40 PI and a very significant number of publications. So how does SERC work? Well, SERC is based on 3 pillars. So on one hand, you get the application area. So, well, theoretical chemistry would be one of them. There is climate. There is plenty other application area, and they are helped with 2 other pillars, which is the infrastructure. So, namely the supercomputers that we have, and the core is science. So, and visualization is actually part of this core e-science. And in the middle, well, there is what we call the e-science cloud that help to communicate between those 3 pillars. And as I said, the bottom pillar, so the core e-science and the infrastructure help the application area to work on different projects. So in the next phase of SERC, the things were reorganized into multidisciplinary collaboration programs, and my collaboration with the visualization people started like this. And it's this MCP that we are part of. It's called Visual Data Analysis. So as I said, I'm a theoretical chemist, and this is the set of tools that we can use depending on the size of the system that we want to study and the time of the system, for how long we want to study it, I would say. So if we want to talk about large system, now we can model system up to millions of atoms and do simulation up to microseconds. And of course, that would concern only the atomic structure. And if we want to go more in detail, well, we have to use quantum chemistry. So molecular mechanics that we use for large system, we just consider just the atomic structure, and we will consider that the electrons are localized on an ideal place around the nuclei, and this is based on the second on Newton's second law of motion, actually. But if we want to have information on the electronic structure, then we need to go to quantum mechanics and use the famous equation of Erwin-Schrödinger. And in this case, we're going to study both the nuclei and the electrons. And in like that, we have access to the electronic structure of molecule, and we can study, well, reaction, but we can also study absorption and emission of light of those molecules. And in the middle, if we want to combine those two approaches, well, there is the QMMM method, so for quantum mechanics, molecular mechanics, that was awarded the Nobel Prize in 2013. And here, well, this is basically taking the best of both worlds. So we can study a chromophore using quantum mechanics, and we can consider the environment, so here a protein, with molecular mechanics, so to see like that what would be the impact of the environment on the electronic structure property of a given molecule. So I will now start to talk a bit more about the application of my research, which I've been working on for like almost 8 years now, and this is related to amyloid diseases. So you probably know that amyloid diseases are connected, so there is many of them, and you all heard about Alzheimer and Parkinson's disease, and they are related to the formation of aggregation of misfolded protein into the brain. So of course this process takes time, and the more that those proteins are going to aggregate into large plaques, and the more the disease is going to advance, actually. So if we focus on Alzheimer's disease, and if we look at the brain, well, so we use the neocortex, the limbic system, and the reptilian brain. And actually those misfold of protein, of tau protein, are formed in the limbic system, while alpha beta are formed in the neocortex. And in a healthy brain, well, those misfolds happen, but then they are flushed by the system. But when the disease happen, well, then they're gonna aggregate more and more and will not be flushed by the system at an early stage of the disease. And when the disease advanced, what happened is like the alpha beta, the tau is gonna migrate to the neocortex, while the alpha beta aggregates are gonna migrate to the limbic system. And at this stage, I mean, this happens at an advanced stage of the disease. So hopefully, I mean, obviously, what we would like to do is to be able to follow this protein aggregates into the brain, and do it a long time to be able to follow the progress of the disease. So how can we do that experimentally? Well, what can be done is that we can use fluorescent molecules, and we can use mice, and we can create a cranial window onto the skull of a mice, and we can inject some molecules, different molecules, that will emit light in different colors. So here you can see an example of two different molecules. So you can inject those molecules in the tail, and after some time you would see those molecules passing the brain-blood barrier and reaching the brain and accumulate on different aggregates inside the brain. So you can see that if we can design molecules, specific molecules that will target the tau aggregate versus the alpha beta, the A beta aggregate differently, well, like that we could get an imaging of the brain. And this is what you can see here, where some aggregates appear in red that correspond to this molecule, and some in yellow, which is more a mixture of both molecules. So the question for us doing modeling is, well, what are those binding sites? Where does those molecules bind to the tau protein? How is the spectral property of those molecules changed by the conformation and governed by the change of conformation when the molecule bind to the protein? What are the conformational characteristics when bound, of course? And of course, can we design probes? So can we design probes with different color? And this we can do. Our experimental colleague have synthesized around 100 molecule that reach from the red to the green, actually through blue and so on. And on a theoretical chemistry point of view, what we know is like the absorption and the emission of those molecules are gonna be largely governed by the planarity of this molecule. And we can define a planarity parameter that's going to depend on the dihedral angle, like this. For a long time, we didn't really have a good structure, PDB structure of the amyloid beta or the tau aggregates, actually. So for sometimes, our only way to rationalize results was to reflect only on the conformation of the molecule and playing those parameters to get insight on what's happening. And what we find out is when aggregates to the protein, there is an increase of planarity, which we can easily understand as the molecule getting on the surface will get more planar. But this changed quite a lot in 2017 with the progress of cryo-EM, where we finally were able to get some very nice structure that were published in Science and Nature for the A beta and for the tau protein. And they have generally quite the same structure. So you get a C2 axis of symmetry here, and they form long helices like this. So they have generally more or less the same type of organization, but of course, the local amino acids and the pockets available are gonna create different sites for different molecules. So when we wanted to study that, when we had this first structure of the A beta in 2017, well, we decided to build a box like this one. So we have 100 molecules, the same molecule I showed you before, the polythiophene molecule, in a quite large box. So we have something like close to 3 million atoms. And we can perform long molecular dynamic simulation. So here we have done more than 23 nanoseconds actually. And if we would like to analyze those results, of course, there is many things that we would like to look at. We want to look at the planarity of the molecule. We want to look at the distance to the protein, to the A beta. We want to look at the specific Coulombic or van der Waals interaction between each molecule and the protein. And ideally, we would like to be able to look at all those data and combine the visualization and the statistics together and be able to interactively play with it. So we started to collaborate with the group of scientific visualization here in Norrköping, and this is what they came up with. So this visualization was hard-coded, specific to our problem here in the Inviwo framework. So here you can see that we can navigate through the timeline of our dynamic. You can see that here we get some distribution that corresponds to distribution of dihedral angle for the molecule, the 4 dihedral angle between the 5 rings of our molecule, and this is average for all the molecules in the box, and we can derive a planarity parameter. What we can do is we can also filter here to see the Coulombic, to see where we have strong Coulombic interaction between each molecule and the probe, and this is highlighted here with the red density, as you can see. So by applying the filter, the distribution can be updated. As you can see, you can hover through the distribution to see the parameter. And you can also select a specific molecule by double-clicking on it. And here you can see, so the statistics that is only for this given molecule and double-click, and the gray zone in the timeline correspond of the results that fits your filtering. So here only the strong Coulombic interaction. So here you can see the density only for this given molecule. And if we reset the filter, well, now you would see the density for the molecule throughout all the simulation. So that's basically the trace of the molecule, where the molecule has been in the simulation box. And you can also play with all the parameters that you have, like the frame range, the Coulombic, the Lennard-Jones, and also what we did also is we derived the absorption spectra based on the fitting of the dihedral. So when the visualization group, when Robin actually came up with this visualization, I was very impressed. And to me, that was a completely new way of analyzing the results and looking at your simulation. And of course, we really wanted to continue this project and make it more generic, so you could basically read any trajectory from your simulation. So just before I continue about the software development, what was very good with this simulation is like it was very easy to identify the site, the binding site for our molecule, as you can see here along the fibril. And if we look more in detail now, what we see is like we have two groups that are hydrophobic. So this one and the blue one here, the valine and the phenylalanine, which accommodates quite well the hydrophobic backbone of our molecule here. And we also have some charge group with the lysine that are charged plus and will, of course, interact favorably with Coulombic interaction with the carboxylate group of our molecule. And after this identification of the probe, we were also able to perform QMMM calculation to look at the absorption of this molecule when bound to the fibril. So that is an average spectra that we calculated for the molecule in water, and that we calculated here for the molecule when bound to the protein. So here you see that we have a significant shift that is matching very well the experimental one, and you can see also that we have an increase of planarity when the molecule is bound to the protein. Also, what was very interesting here is that we find out that the effect of the environment is actually minor for the absorption of the molecule, and the main change that we observe here is due to the increase of the planarity and not to the environment. So, as I told you, after this first implementation that was done in Invivo, we thought that was very interesting, and we wanted to continue this effort and make it much more general, so you could basically read any trajectory. And this is what we started to do 2 years ago. And we wanted to develop this software for visual interactive analysis of molecular dynamics that is available on the GitHub here. You will see the link again at the end of my talk. So what is the idea? Well, I mean, the idea is to change paradigm, because for a long time, this is how I was working with my molecular dynamics simulation in an iterative fashion. I was looking at the visualization of my trajectory and looking at statistics that I could gather with my MD program, for instance. And I was going back and forth like that. Well, and obviously here there is a problem, because the trajectory that you are visualizing might not exactly correspond to the statistics, and vice versa. And obviously you would like to be able to do it in an interactive fashion and be able to combine the visualization in an analysis in a single software. So how does it work? So this is a short movie presenting the general feature of AMD. So you can load a file, so it can be a PDB file, multiple PDB file, or a GROMAX plus XTC trajectory. By double-clicking on the molecule, you're going to be able to recenter it. You can change representation using keywords that are well, quite standard, I would say. We have licorice, ribbons, and different representation. You can color your protein backbone in form of the secondary structure, and you can calculate properties. So I can create a new property that it was going to be, for instance, here the distance between two atoms. So I can just right click on the atom I want to and select it, and go to the second atom I'm interested in and select it also. And then I can click on the S to show this distance. So I don't know if you see it here, but there is a thin line that connects those two atoms and that show you that this is the property I'm following right now. I can look at this property in the timeline, and I can look at this property also at the distribution of this property. And I can filter through the distribution, and you can see that there is some zones in the timeline that becomes gray, and those zones fits the parameter. So if I click on them, you would see some conformation that corresponds to very short distance between the beginning and the end of my peptide, oligopeptide. I can also look at, I can aggregate properties. So here I would look at what is the distance between all the carbon, all the CO. Basically, I will look at the CO bond here, but at all of them for all the alanine at the same time. So you can see here that I showed here. So this bond is now shown on the screen, and here I get the distribution for those aggregated bond lengths. I also have a dynamic frame window. So here I would just look at the statistic for this for this selection, and you can see it's highlighted in blue. The blue one is the one for the full trajectory, and the yellow one is the one just for this dynamic frame window. We also have a Ramachandran plot, as you can see here, and what you can do is you can do a selection in the Ramachandran plot. So if I do a selection in the Ramachandran plot here, you can see that then it will be highlighted here and here on the screen, and vice versa. I can do a selection on the molecule that will be then highlighted in the Ramachandran plot. Yes, so that's the basic feature of VIMD. I just wanted to introduce with this video, and well, now I will focus on the remaining feature, and one that we developed is we developed a selection tool. So you know, in molecular dynamics, that you can use textual queries or spatial selection or feature space filtering. And usually how it's done is by combination, also using Boolean. So for instance, you want to have the res name alanine and not a label, for instance, or you want to have a backbone within the distance of a given residue, for instance. So our selection tool that was presented last year in the MolVA workshop, actually, so propose a seamless combination of selection paradigms used in MD simulation, combined with morphological operators, because you might want to be able to grow your selection through a covalent bond or through space, actually, and also provide an immediate feedback to the user. So here I got a series of videos that explain that. So for instance, with a shift click, you can select one, and the right shift click, where you can unselect something like that, and then add on later to your selection if you want to. If we look at this, how to grow selection. So for instance, if I click here on this amino acids here in the middle of my beta sheet that is on the surface, and I can grow this selection using either a radial growth around my selection, but I can also use a grow along the covalent bonds, and then it becomes orange, and when I validate my selection, it will become blue like that, and my selection will become blue. So I can follow my selection that is here in the Ramachandran plot with the evolution of my dynamic. So here what you see is a beta sheet form of alanine, and we get side chains here, and they are on a hydrophilic surface. And what happened when you start the simulation is you have a very nice beta sheet, but when you accelerate, you would see that this beta sheet breaks, and you arrive with the normal, only few remaining amino acids that were selected at the beginning in the beta sheet, while most of them here are in an alpha helix or in the random code. You can see here also the selective, the feedback from the selection that you can do either on the Ramachandran plot or on the 3D view to follow your selection. So this selection that you have done can later be used, and we are illustrating that with another data set here. So this is an aspirin inside its protein. So if you would go and select your molecule here, we'd be able to grow using radial growth, actually, and you can save this selection and use this selection later for a specific representation, for instance. And another thing that you can do is use this selection not for representation, but for property calculation. For instance, you might want to calculate the distance between this molecule to the pocket here. So the selection would be your pocket, and you want to see the distance between the center of mass of this molecule and the center of mass of this pocket that has been defined by your selection. But you also want to be able, you could in principle be able to follow the RMSD of your selection if you want to, or any other property for that matters. So the last thing I would like to tell you about, and this is the latest development that we made in VIMD, and this is for structure tracking and spatial distribution function. So what we develop is an interactive recentering of the molecular trajectories using internal reference frame. And this structure centering will allow to aggregate an efficient aggregation of the spatial distribution function for molecular structure for ensemble simulation by overlaying different molecular instances from the ensemble. So what we have is, first of all, we have a shape space plot here that will tell you if your system, well, at least if your if your reference frame has more linear shape, or a 2D shape, or a 3D shape like this, and you can follow the shape of your structure with time, with the green points representing early point in your dynamic and white point representing late point in your dynamic. And what we can do is we can also, with a very simple right click, recentering live, directly here and without using any empty engine, you can like that recenter your trajectory. So here what you see is 3 snapshots occurring with time, where here the trajectory has been centered on the protein, and you can see that the molecule is getting the aspirin molecule is getting inside. And here we have, so this is exactly the same frames here and here and here, but we have here we centered the trajectory onto the aspirin. So you would see all the protein moving and getting around the molecule. So of course this is very interesting to be able to recenter like that your trajectory and doing it live. But it's also open to many features. And for instance, if you would like to see, let's say you have a dynamic with a molecule that will interact with your DNA, right? And let's say that everything is moving in your box because you haven't recentered your trajectory and so on. And if you look at the density where this molecule has been in the simulation box, well, it's going to be all over the place. But if you use the DNA as your reference frame, suddenly you would see that a very clear identification of the pocket. And here we will present an isosurface probability, where the transparent one represents low probability and the pink one represents the high probability. So this is working for DNA, that is pretty stiff, I would say, but this is also working for smaller protein system, as you can see here. And if we look at the system in the reference frame of the simulation box, well, I mean, you cannot really see anything, but if you then start to use the reference frame of the protein, it becomes suddenly very, very clear where the molecule is staying onto the protein. So that's a very interesting feature, I think. So what we do if we want to calculate a property is we will aggregate the statistics with time and also with the number of molecules. So let's say that you have 50 identical molecules in your system. So here this is para-nitroalanine molecule. So I get 50 of them in a box. And I can superpose them. So I can superpose all those molecules for each frame here. So if I have n frames and m molecules, so here I would have m molecules superposed, but I can also superpose each molecule for the n frames. And at the end, what I can do is I can have a spatial temporal superposition and aggregate the statistics for n times n being the number of frames, and m being the number of molecules. So if I look at this system here, so this is my para-nitroalanine system. I get 50 of them, I get water, and I also have some ions here. And this would be the spatial density distribution of oxygen, of the oxygen of water around the PNA molecule. And if I aggregate the statistics for the n frames of my system for one given molecule, this is the density volume that I obtain and the isosurface that I obtain, which is extremely noisy, and we cannot really see anything from that. But if I then suddenly look at the 50 molecules and for the n frames, then I aggregate my statistics, and even with short dynamic, I can get a very nice density volume here and equivalent isosurface here. So that's very practical thing to do. It allows us to aggregate all the statistics quite easily in the VIMD software. So here I want to illustrate that using a larger system, as you can see. So we're getting back to my amyloid fibril system from the beginning. And so here what we do, so you see the full system here, and we're going to create an ensemble. We're going to create an ensemble that will be composed of chain one being one of the beta sheet. And since they repeat each other, we're going to be able to aggregate the 252 chains that you see onto a single one. You can do that by superimposing them. So here it is. Then they are all superimposed here. And you can see, so even though there is a twist and so on, I mean, we can superimpose them like this and see how the backbone of the 250 chains behave along the fibril. And then what we want to know is we want to be able to look, to apply a density filter. So this is what we do here. And we just, as a density filter, we're going to use the molecule, so the PFTA molecule that is in our system. So here we compute the density and we can plot it. And here you see where the molecule has been and along the fibril, and everything is aggregated onto one single image. So you see on top, this is the pocket that we have identified before quite clearly. But was very nice when we developed this feature, and we didn't observe before and didn't know even before, is like there is also a pocket, of course less probable, but there is a strong interaction between our molecule and this fragment here, which is also positively charged. So, but that was quite interesting, because with these two, we discovered this pocket that we didn't even find out before, actually. So this aggregation is very powerful. So I think I'm going to be close to the end of my talk. I'm a bit ahead of time, but since we are late, I think it's pretty good, and we'll have plenty of time for questions. So, so to conclude, the generic framework, VMD provide a generic framework for analyzing molecular dynamics simulation. For the moment, we can read PDB file, multiple PDB file, and GROW file, as well as XDC file for longer trajectory. We have combined selection paradigm for MD analysis, providing visual feedback of the ongoing selection. We have interactive property definition, aggregation, exploration, and we connect visualization and analysis in an interactive fashion. So you can find the software, the binaries, not the binaries. Well, you can pull the software and compile it. It's available on GitHub. We are, of course, actively working on it, and there is a lot of things to fix before release. The main issue that we are facing is to improve the language for the property calculation to disintegrate if we want to do a one-to-one operation, one-to-n, or n-to-n. We need also to have an interface for saving the calculating properties and distribution to an ASCII file probably, or a CSV file. And of course, in the long term, we would like to be able to couple it to an MD engine, for instance, Chromax, the Chromax API. That would allow us, well, not only to perform minimization, but also by reading energy file to be able to filter according to specific energy terms and be able like that to go into more detail into our analysis. And of course, many other ideas that we have and that you probably have, so I will be very happy to hear about them later during the question. To finish, I would like just to reflect a bit. So as I said, I joined the group in 2018, coming from being a theoretical chemist and joining the visualization group. That is a very interesting adventure. And I just to reflect a bit on that, I think that having a domain expert embedded in the visualization environments can be very interesting to provide. So, of course, domain-specific knowledge, but also to allow rapid prototyping and to provide immediate feedback on this prototyping, making sure that the tool and interface is useful for the community and used by the community, and obviously to expand the research horizon. Finally, I would like to thank a lot the group of visualization in Norrköping that welcomed me since 2 years, and give a lot of thanks and praise to Robin, that is the main developer of YAMD. This is his PhD project, one of his PhD projects, and he has been doing a fantastic job. Martin, Anders, and Ingrid. The theoretical results I presented have been done in collaboration with the group of Patrick Norman in Stockholm, with major contribution from Caroline Schenning and Kevin Gustafsson. For the experimental parts, so those molecules, those fluorescent markers are developed in Linköping by the group of Professor Peter Nilsson, and the characterization, the fluorescence and so on, is performed by Mikael Lindgren in Trondheim in Norway. I would also like to thank the group of theory and modeling at the LOE. So this is the full LOE, this is not the group of theory and modeling. For where I spent 50% remaining of my time working with, and we are working on different projects for organic electronic, and I invite you to look at the LOE website if you want to learn more about that. The finance from LIU and from the Swedish Research Center, the Swedish National Infrastructure for Computing for Computer Resources, and of course you for your attention. Thank you. Jan, cannot hear you. Should I unmute the Discord?
Okay, thank you, Mathieu, for this great talk. Since it doesn't really make sense to clap in this virtual environment, maybe we can send some nice smileys into the chat, so Mathieu knows that we really like the talk, because I think it was great. If there are any questions towards Mathieu, please feel free to write them in the chat, and I will ask those questions on behalf of you. But to give you some time to ask those, maybe I have a few questions on my own. I will start with the really generic one, because you have a nice opportunity, or I mean, you are working in both, right? I mean, you are by training the chemist or the domain experts, as we call you guys.
Yes.
But you also get an opportunity to work in the WIS group, so you know the both sides quite well. And I was wondering what you would perceive as a current challenges for us, for the visualization community, how we could help you even more. I know you have now presented some work you are doing in this regards with respect to molecular dynamic simulations, but maybe on the broader scale, what are the challenges you see and think that would really help you if we could figure out some nice solutions for you?
Well, okay, that's a big question. Well, well, to me, I think that the main challenge for the visualization community is to get their work known to the domain expert community. I see a lot of very nice work done in your group, for instance, Jan, or in other group, and I feel that it has a problem to reach the theoretical chemistry community, and I think it has to do mainly with the fact that most of the visualization contribution are published or presented into visualization conference, and maybe not in proceeding of those conferences, and not in the theoretical chemistry, not as much in the theoretical chemistry journal. So I think that's one of the challenge, and the other challenge is, of course, to make the meeting tool developed in the visualization community available and maintain, which is of course a big challenge, right? I mean, that's one of the big problem, to make those tools stable over several platforms and to be able to ensure the distribution, but also the manual, provide support. This is where the main challenge is, I believe.
Yes, I mean, you're definitely right that publishing is part of the issue. That's, after all, why we're trying to set up this small workshop. But yeah, I mean, thanks for the answer. We will try to do our best in order to remediate this issue. Hopefully, in the future, this can work out. I have now some questions from the audience. Otin is asking, what is the size limits in terms of the number of atoms for the VMD, I guess?
The memory of your computer, I would say, mainly. Yeah, I mean, as you can basically load. We can load trajectory up to several gigabytes without any problem on a laptop. So in terms of atoms, I cannot really answer this question, but I mean, I don't think it would be problematic to display a million atoms. If you just have one frame, of course. But I mean, basically, that's going to be the memory. I mean, the RAM of your computer, so you can load the trajectory. That's basically the limit, I would say.
Okay. The other question was whether there is any support for coarse grain simulation or different trajectory formats such as LAMPs.
Not yet. I mean, this is also in the perspective. Of course, we would like to extend that. I mean, well, basically, you can read a PDB file. So if you create a PDB file with your coarse grain, I mean, you can read it. That's fine. But we don't have any support for LAMPs or Amber, which would be of course, the two next thing to implement in terms of file formats. Because with Chromax, Amber, and LAMPs, we would cover probably 90% of the MD software. So that's of course something that we want to do. But I mean, there is many things that we want to do, and not as many hands to do it. So yes, but yes, obviously we would like to extend that to other file formats. That would make a lot of sense, and that's something that we would like to do in the future.
And actually, a connected question to this is that whether it's possible to connect your tool to the running simulation to do some kind of in situ analysis.
Yeah, that's also something that we would like to do, obviously, and since the Chromax is part of the CERC initiative that I talked at the beginning, actually, we really want to go in this direction, and we'd like to be able to couple it to the Chromax API. So like that, we would be able to perform minimization, but also very interestingly, I think, is to read the energy file. To read the energy file, so like that, we would be able to do also filtering in function of the energy terms. That would be great. We are looking into this direction. One solution might be also to have VMD running on the cluster, actually. That would help a lot, so like that we wouldn't have any problem of file transfer of heavy energy file or trajectory files, actually.
There is a subsequent commentary running on in the chat. Xavier is, for instance, asking whether you have to load the whole trajectory or simulation into the memory, or Bjorn is asking whether you can skip some frames.
That's also something that we wanna have, that we have been thinking about. We don't have for the moment, but basically when you would start to ask to load a trajectory, you would be able to. We want to have that possible. For instance, don't load the water or load only frame to this, frame to that. I mean, an interface that would tell you, okay, this is what you have in your system. What do you want to display? So like that, we would be able to indeed save time. So that's a very good idea, and we thought of it, and that's something that it's definitely in our to-do list before we can release it in a more general way, and also hopefully publish it in a theoretical chemistry journal, as I was saying, so people could have access to it.
Yeah, I mean, this could also be really useful, I guess, in terms of computing the properties as you showed us, right? Because
yes.
Now you need to analyze the whole trajectory, and meaning that if you need to analyze every single frame and you have a long simulation with hundreds of frames on the nanoscale, that means that you need to analyze all these frames to compute your properties. But if you could do some kind of a coarse grain analysis, you could get a still overview of the whole simulation, but in the relatively shorter time.
Absolutely. Yeah, that's a very good point indeed. Yeah.
Okay. Thank you once again for the great talk.
Well, thank you very much for inviting me. It was a real pleasure to be here, virtually here, and tell you about this work. And well, thanks a lot.
So if there are any more questions, everyone is definitely welcome to stay in the Discord channel, and we can still talk there and discuss offline during the coffee break. But at this point, I would switch to the Bjorn's talk, because it seems that we don't really have the second speaker ready yet. So I think the Bjorn can now tell us a little bit about his work on the vesicle simulations. So we are setting up everything. Just a moment, guys.
Yes, can you hear me? Does it work? Oh, okay, excellent. Okay, so should I just start right now?
You can start right now.
Okay, thanks a lot. Yeah, great to be here once again, this time virtually. So today I would like to talk about our vesicle builder. This is actually a project which is running already a little bit since a longer time. So basically you will see that a number of collaboration partners and students were involved. So especially Beatrice, Manuel and Jan developed the prototype. And then were a number of collaboration partners involved, like like Jens Krüger and Alejandro Giorgetti from Tübingen, and Alejandro is actually from the University of Verona. And today I want to talk about the vesicle builder, which is a membrane plugin algorithm for the cell microcosmos membrane editor. So let's first dive into the membrane editor for those of you who don't know this small piece of software. So basically, the whole idea of the membrane editor is based on the idea when it first was published circa 9 years ago, that you create membrane models based on the fluid mosaic model, which basically means you have a two-dimensional layer, so like a rectangular layer, which was in the old days most recently always simulated and visualized for MD simulations, for example. So you have this two-dimensional layer and you use it to distribute molecules on top of this layer. We call this a 2.5-dimensional knapsack packing problem. I will not go into details why it was a knapsack packing problem, but this is more a theoretic description of that, but please look to the initial paper if you want to learn more about this. But basically the idea was distribution on a two-dimensional area, but you have the collision detection operating on the three-dimensional atomic structures of the lipids, which you can see here. So, and this is why we called it a 2.5-dimensional approach. Other features of the membrane editor, which are now important in this context, of course, it's an open source Java project. It's what you see is what you get membrane modeling tools. So this is a difference to what you know, for example, from Sham-GUI membrane builder, which you can also use for other purposes, or for example, the PACMOL software. Then you can use protein placement via OPM and PDBTM. You can import and export custom PDB files. So you can set the lipid composition based on percentages or absolute numbers. We bundled the JMOL viewer with the software. Important for what I talk about today is that you can create microdomains. So you can draw small areas and change the composition of lipids inside this area. You can stack multi-layers, so you can make it all on one single layer, or you can stack multiple layers on top of each other and have different membrane compositions. And you can use a membrane packing algorithm interface to generate and explore new membrane packing algorithms. And this was actually used in this project. So this basically means for the vesicle builder, what we had to do, what you see here, this is basically the membrane editor, where you can see on the left side here the different lipid types with the composition and the ratio, which was used for the lipids. In the center, you see the abstract visualization based on the crystal-like visualization of the different lipids. And on the right side, you can actually see what is the actually achieved number of lipids inside your membrane. So what we had to do is to transfer this 2.5-dimensional packing approach to a 3-dimensional packing approach. How did we do this? For most of you, it's not a big secret how you do this. So we basically use the polar coordinate system, which you can see here. and used it to transfer our coordinates to the Cartesian system. So you can basically see here, so x, y, and z are each the Cartesian system coordinates, and then we use the semi-axis. This is basically what you see here to generate a 3-axial ellipsoid. So we were able then to use a semi-axis A, B, and C in combination with the angles theta and phi. So the whole thing is around a center point here. Around this, the vesicle will be distributed. And of course, you can define then the position on the surface of the sphere based on the radius and on the angles phi and theta. So what was important for our approach is we needed to estimate the area per lipid for each lipid. So basically just a 2-dimensional intersection. So it was not so important to look into the 3-dimensional area because we have this sphere-like surface on top of which we are distributing the different lipids. So inside the membranature, we are using then for this purpose now the Knut-Thompson expression, which we use to approximate the surface area. And basically, we can also use we have 2 different options to estimate the area per lipid for each lipid. One is the radius of the lipid projected onto the 2D surface of your sphere. And then the second one is that we use the bounding box of the x-z coordinate and then divide it by 2. And we take the smaller value of this. So this is basically internally how we compute this value. So the next thing, what the algorithm is doing, if you have more questions about this later on, I have another slide, which is more going into detail. We have 2 phases. The first one basically utilizes a random placing algorithm, which we implemented already for the original membranator, but then just on a 2-dimensional area. So in the initial phase, just lipids are randomly placed using this polar coordinate system on the surface of the sphere, which is basically done then in runtime n. And then in the hybrid phase, we are starting, so you have already a well-populated area of lipids. In the hybrid phase, then we are trying to add new lipids. And then to get more space inside the membrane, the lipids are approaching the different poles, so the top pole and the bottom pole, more specifically of the vesicle. And on the other hand, there's the shaking and twisting period implemented in this. And this has a runtime of n log n. So let's have a look at the GUI so that you get an idea what you can do with this vesicle builder. So the nice thing is, first of all, we have a very simple approach, the so-called vesicle builder rookie mode, which you can basically use. You just need to type in the different dimensions of the 3 different semi-axes, and then you can directly press on OK, and it starts generating your vesicle. But if this, so you also see that you have here an estimation of the area per lipid and how many lipids you can distribute on top of this membrane. So what you can else in addition do is basically you can use the vesicle builder pro GUI, which has different options. So you can change the termination mode. For example, the proposed lipid number is actually computed by the membranator based on the Knut-Thompson formula in combination with the area per lipid estimated for each lipid type. But you can say you want to reach a specific number of lipids, so you can put in here the absolute value, or you can say just do not terminate, then you will run forever until you basically press stop in the generation process if you want to have a very densely packed membrane. Then you can define the center point, so the point 0 for the vesicle. To, for example, especially if you use multi-layers, you can distribute in the 3D space. Then you can change the alignment of lipids. So normally it's aligned, of course, to the surface normal of the sphere, but you can change if you need it for specific purposes. You can change if it's rotating along the z-axis, and you can, of course, also choose to make only a micelle for the generation. And you can, what you also can do is you can, so if you add lipids on top of the surface, you have a number of failed tries. So you can set this number of failed tries when the algorithm actually stops. And then you can change the hybrid phase scheduler, which is basically used to distribute the lipids on top of this membrane after the initial phase. And you can change, for example, if you want to use a shake approach, the approach poles and the twist approach, which I mentioned already earlier. So, and the other interesting thing is that you can have an overview of the area per lipid approximation for each lipid type. So you have here an average, but you can also plot it out for every single lipid type. So let's have a short look through the different shapes which you can generate with this approach. So for example, here you see a simple ellipsoid, and what you can see here that you have different colorings here. So basically this is used by combining the microdomain approach with this vesicle builder. So you have on top of the vesicle builder here a small microdomain, and then both parts are subdivided, also generated with different lipid types. So each of them can have a different lipid composition. Then you have here, for example, two vesicles which are fused. This is a, so to visualize the fusion process, you might have to, again, this is used by using multiple layers, but you might have to delete them manually with the membrane editor on the intersecting parts, some of the molecules. Here you see, for example, a tilde-like membrane, which has a wave-like structure, and basically you can combine different spheres, again, with the microdomain approach to limit the area on which the lipids are distributed, and then you have this very nice wavy structure. You can also here, for example, make a very large sphere, and then only so define a microdomain which is used to say that only here the lipid should be placed, to limit the amount of lipids placed. And what you also can do, you can generate cylinders, for example, by setting one of the dimensions to a very large number. And what we basically did here is, so we have in the center, we have a tube, and then on two parts on the outer skirt, we have basically then two half spheres that are attached to it. And what you also can do, you can stack different lipids and liposomes inside each other. So basically we have here unilaminar liposome, which is, micelle, which is inside a liposome. So two of these micelles inside the liposome. What we also tested is if we can use relatively large structures. So this is a structure with more than 2 million atoms. So we have 50,000 lipids on top of each. This, for example, is something you cannot, if you have ever used, for example, the Sham GUI vesicle builder, you cannot do this because it's in the browser and it is quite limited, the amount of lipids which you can add there. You can see here that it's important that you have a good computer with a lot of RAM. So something similar to what you heard before about the software which was presented before from Matthew. So this was 32 gigabytes of RAM to store all the three-dimensional structures and then export it to a PDB file. So we also made a first very simple test MD simulation. This was basically done manual. And we had a composition of cholesterol, DPC to POPE, 32423. So we had around 2,000 molecules on both sides and a radius of 75 angstrom. We used GROMAX4 for this approach. You see that this is not the most optimal vesicle which you want to achieve, but of course this is just an early approach, so you can improve the protocol in this. This was something which somebody did who never used GROMAX before in just a short amount of time, so it was a very well done job here. And basically he puts the whole structure inside a water bath, used the VMD TTK script to remove the water inside the layers, and afterwards this was simulated for 10 nanoseconds, and it was stable, although you can see that it was shrinking a little bit in the beginning. So this means to improve this, for example, you can try to increase the area per lipid on this approach. So let's have a short look at the outlook. So we are working now on different algorithms based on this vesicle builder, which you can use then also to generate other shapes. We are working on the improvement of the membrane editor. I just uploaded yesterday a new version of it, and especially what we did last year is that we integrated Java 7. So now it's also possible to run it again on Mac, because there was a problem with Oracle with Java 3D in the past. It did not work anymore. And we are working on new simulation protocols for vesicles. With this, I come to the acknowledgement. So basically, the initial part of this work was done during my time at Ralf Hofestedt's group in Bielefeld. So thanks a lot go to all the students who worked on this, especially Beatrice, who did her master's thesis on this work, and Manuel, who worked on this on the simulation, and Jan had developed the early prototype on this. At the moment, I'm basically working on this algorithm. We were supported by Erasmus and Erasmus Plus to do this in collaboration with Verona University. We simulated this at the RWTH Aachen and the Paderborn Center for Parallel Computing. Yeah, and thanks go, of course, to all the other students. At the moment, we have ongoing current work with Falk Schreiber from the University of Constance and Monash University, Jian Li and Jian Zhu, where we are working on different protocols, not just physicals, but basically also based on the membrane editor, where we simulate different membranes in the context of molecular modeling. And with this, I'm at the end. Please download here the physical builder, and we can make a test phase, or if you're interested, we can also have a small Zoom workshop later on. Just let me know. And with that, thanks a lot for your attention. I'm open for questions. I don't know. I can meanwhile try if I can share. Let's give it a try. Maybe it completely fails. Aha. While I'm waiting for questions, this is basically how you start the physical builder. And you can see here that I have here already defined the different lipids. Basically, I just have to click. You see that this is now 69 angstrom currently defined. I just click here on OK, and then it starts to generate my membrane.
It looks great, Björn. Thank you very much for the talk. So there are already some questions coming in. So for instance, Mathieu is asking whether you're planning on enabling the insertion of protein on the surface of the membrane.
Yeah, so this basically works already for normal membranes. So the membrane editor was developed for this purpose. So we used PDBTM and OPM for this purpose. At the moment, I have to say the actual version of the OPM implementation, I just checked it yesterday, it does not work correctly anymore. I have to fix this. But so for the physical, this is not completely working at the moment. What you could do, I just stopped this here, is basically at the moment, if you only have to insert a single protein, and this still works, the trick would be, I think, that you just try to move the physical down here to the bottom area, and then you try to insert it. You can do it manually in any case. So manually you can do it, but this is then, if you want to use the information from the databases, then you would have to do some tricks with that. But so yeah, that's also planned in the future that we it should be not too hard to make it work here.
Mm-hmm. Great. There's also a question from Auten whether you support a different files, for instance, a file format such as CIF instead of a PDB.
No, so we are just supporting PDB because basically what I learned, you can nearly all structures you can export to PDB, yeah, so this is why we so at the moment we did not integrate other formats than PDB.
Mm-hmm. Xavier is asking whether there is some possibility for parallelization if you, for instance, put back the lipids in the different parts first and then combine this together.
Yeah, I mean, basically, so we once created an algorithm with a previous project, which was also using parallel computing, but in a very simplified way. So it basically worked. And of course, so basically we could improve this algorithm. So we have also some other packing algorithms which were making use of this parallelization, which was more based on just two-dimensional placement of lipids. But we could use some of these approaches in the future, yeah. But it will be anyway, it will be open source. So if somebody is interested, we can also just collaborate on this and expand this approach.
Great. I have also one question on my own. So maybe this is not really biochemically relevant, since well, one step back. I wanted to ask whether it's possible to use your approach to pretty much create membranes of any shape, not only the spherical or ellipsoid types, and this might not be really biochemically relevant as due to the surface tensions and so on, but I was really wondering if you can create a random blobs of a different surface shape and just populate this surface with the lipids.
So basically what you cannot do is that you just import a mesh. For example, what I could think about that you create a mesh with Blender, and then you import it to the membrane, and then you can automatically place the lipids on top of it. So this is not supported by now. So at the moment, we just started this approach where we really use this very simple spheroid simplification. But the nice thing is, because you can actually use this, what I just mentioned before, that you can basically just draw here, for example, here a specific area. You can actually do a lot of okay, I have no lipids inside this. So you can actually play around with different configurations, and everything what you can think of, what you could combine with this kind of approach is possible. Let's try this, for example. So here you see now, for example, that he's only placing lipids inside this area, and you could increase this specific area now, or you could increase the size of the vesicle, and then you could add, basically add different shapes of this kind of membranes and expand it, as I showed it in the presentation.
Okay, thank you very much for the answer. If there is any more questions, again, feel free to jump into the Discord channel. Bjorn will be around the whole conference, I believe. Thank you everyone for joining in this session. There was supposed to be one more talk, but we still didn't get in touch with the speakers. So I guess we can end now and have at least a little bit of break before the next session starts in 11 at 11. So yeah, thank you very much, and if you can send some nice smiley to all the speakers again, that would be great. And see you around. Just don't forget that the next session will, I believe, has its own YouTube stream link. Maybe I'm mistaken on this, but you will definitely find out on the program page of the whole conference. So thank you again for joining in.
Thank you. Bye-bye.